you very much for the introduction. So today I will discuss about how we use the acoustic metamaterials to develop new implantable sensing concepts. And because the topic is related to implantable sensors, I would like to start just with a few examples from literature. So the majority of implantable sensors are based on electromagnetic coupling interrogation. So typically we have a resonance circuit which is made by different elements such as an inductor, a capacitor, and a resistor. And then when we apply pressure or strain, one of these elements will change, and this will shift the resonant frequency of the circuit. Now, what do they have in common is the fact that they're all based on electromagnetic waves to excite the sensors. And what our group is exploring is a new concept which is based on acoustic metamaterials and ultrasound waves to develop new passive implantable sensors. This is a very new approach, which has also started to be explored by other groups, such as in this case, where they have developed this metagel sensor to monitor temperature, pressure, and pH in the brain using ultrasound waves. Now, the advantage of using ultrasound waves are mostly two. So the first one is that we can introduce, for the same penetration depth, much lower power level in the body, up to 72 times less, which means that this approach is safer for long-term interrogation in the patient. And then the second main advantage is that this approach is compatible with medical ultrasound readouts to perform echographies. So there is no need also to develop a customized receiving unit to interrogate the sensor. In today's talk, I will start with an overview about what are acoustic metamaterials. I will move to our sensor concept, which is specifically for temperature monitoring in implantable devices for infections. And then I will introduce how our experimental setup looks like, some results for the water characterization in vitro. And then today's talk is the focus on towards a realistic implementation, which means what happens when we had animal tissue and the problem of sensor localization. So starting with what are acoustic metamaterials. You can think about metamaterials as the assembly of unit cells, which when they are together, they make a new material with properties that the bulk material will not have. And in this example, for example, in acoustics, we can have this type of metamaterials which are made of these trusses in this unit cell configuration, with which we are able to open band gaps in the reflection spectrum. So in acoustics, this approach is typically used to perform filtering. And in our case, what we want to do is monitor this peak, the shift of this peak to quantify temperature or potentially other parameters of interest. About our sensor, we use the standard silicon microfabrication technology for the fabrication of the sensor. Deep reactive ion etching to fabricate high aspect ratio silicon pillars, which are disposed in a hexagonal lattice configuration. And then when we interrogate the sensor with ultrasound measurements, we have a reflection spectrum, which typically has a peak around 5 megahertz. And this is like a fingerprint of our sensor. We could also move this peak if we change the dimensions of the pillars. But for this study, it's fixed at 5 megahertz also for the probe that we were using. And then about the long-term vision of the project, so the idea will be to install these acoustic metamaterials on top of titanium prosthesis, because then just by using an ultrasound probes, we can interrogate the sensor with ultrasound waves and then measure back the reflected signal, do an FFT, and just by tracking the shift of this peak, we can quantify the local temperature in close proximity to the prosthesis. And what is also very new at this advantage is that we do not need any electrical component or battery to power the sensor. How do we measure temperature in our experiments? So we have a 5-liter water tank where we immerse the metamaterial on top of some supports. Then we heat up the temperature to 45 degrees Celsius, and we let the water naturally cool down at room temperature. And then we use some thermocouples to monitor the temperature in the tank. Then we have an ultrasound probe, which is connected to an XYZ stage controller. And this allows us to make a scan of the sample, recording the top echo from the metamaterial. Therefore, we get an ultrasound scan. And then in each of these pixels, we have a time trace, which is the reflection from the metamaterial, which we shift with temperature. The first results will be about the calibration in water. And here you can see how typically the FFTs look like for some temperatures. So there will be a shift of the FFTs with temperature. And then we develop an algorithm which is able to extract the frequency peaks that we also use to compute the sensitivity and the resolution of the sensor. We can equivalently plot these FFTs as 2D maps. So here we have the frequency axis, the temperature on the y-axis, and the amplitude of the FFTs, which is represented as a scale bar with colors on the right side of the plot. When we compute resolution and sensitivity, we do it with a normalization with respect to these values T0 and F0, which are the closest temperature recorded to 37 degrees Celsius and the frequency peak of the FFT detected at 37 degrees Celsius. And the sensitivity is computed as a ratio between this quantity delta F, which is the normalization of the frequency peaks, and delta T, which is the normalization, a difference with respect to T0. The resolution is computed as the standard deviation of the residuals divided by the sensitivities, where the residuals are the difference between our experimental data and the linear interpolation of our data. So these are the results in water. And as you can see, I mentioned in the beginning that when we do a measurement, we acquire an area for different pixels. And here you can see the results performing a spatial averaging over a different number of pixels. So the sensitivity is not too much affected by this averaging, while we saw from experiments that there is a significant improvement in the temperature resolution that we can record, that in this case dropped to 40 millikelvin. I will come back on the meaning and the contextualization of the resolution when I will also present the data for the tissue later. Because as I mentioned, so these are interesting results, but we still need to consider what is the effect of real tissue, because in the end, if we want to develop a sensor, we also need to consider scattering and attenuation effects of the different layers interposed between the probe and our sensor. So now I would like to move on to the closer to implantable conditions, which means how the sensor performance change with the introduction of tissue. Here I performed 3 different experiments. On the left side, I have again the water characterization, the calibration for our sensor. In the middle, we have some results with TMM, which are tissue mimicking materials or phantoms. These are materials that you can build in the lab with agar and graphite. And the advantage of these materials is that you can control the attenuation coefficient of these phantoms, and they do not degrade so fast over time, such as the case of tissue. And on the right side, these are the results for animal tissue. And already looking at the results from these maps, we can see that there is a temperature sensitivity emerging from the graphs. But if we look at the FFTs at 37 degrees Celsius, we can see for these 2 cases, first that there is attenuation introduced in comparison to the water case. And especially for the tissue, the FFT becomes much more noisy due to the effect of scattering and attenuation, which are introduced in the tissue case and not in the water case. About the analysis of the temperature performances, so the sensitivity does not change significantly in this case, but the resolution degrades as expected because we have an introduction of scattering and attenuation. And in particular, I have marked this value of 0.1 Kelvin because it's the value that is used by infrared cameras to perform medical thermometry. So typically, if there is an infection, there are some approaches based on infrared cameras which allow you to quantify the outside temperature at your infection site, and the resolution is 0.1 Kelvin. And as we can see, the TMM is quite close to this value, and the tissue is still below 0.2 Kelvin. So at this point, I would like to emphasize that here we did not perform yet spatial averaging, like as in the case of the water calibration. So we believe that when we will perform also the spatial averaging, these results should also improve with respect to the resolution analysis. And then I would like to move to the last part of my talk, which is about the sensor localization. Because once the sensor is implanted, there is also a main problem, which means how do we find the sensor on the prosthesis? Because if this is not done correctly, it could lead to false positives with a bad impact on the prognosis of the patient. And also, if you look at ultrasound images, there are some artifacts arising due to the speckle artifacts in vivo, which make also the localization even more difficult. Typical approaches are based on imaging improvement techniques based on X-ray fluoroscopy and deep learning, which are approaches quite complex to implement. And in today's talk, we have explored the simpler algorithm to find the localization of the sensor without using any marker. So the first approach is based on the root mean square of the full time signal in the three different cases. So this is an intensity map which plots the root mean square value for each pixel. And as you can see in the water case, we can still distinguish a bit where the water starts. But in these other two cases, it's a bit difficult to find the sensor. Then the second case is based on the windowing approach, which means that only one part of the time signal has been performed the root mean square value. And here you can see that we can much better distinguish the edges. However, still in the case of tissue, it's still difficult to find the localization of the sensor. And the last approach is based on the spectral analysis. So here the main difference with the other approaches is that we use the FFT from the sensor, which I mentioned is specific to the metamaterial, which shows this peak of 5 megahertz. And here what we did, we defined a threshold with respect to the peak, and we counted the number of samples falling below this threshold as an intensity color. So if there is no peak, the map will be black. If there is a peak and it's very pronounced, the map will be very bright. Let's focus now on the last case, which is also the more interesting. Here I have compared the different localization on the map. So if we go on the very edges of our area of interest, where we also do not expect the sensor to be, we can see that the FFT is flat. If we go on these 2 points, which were some points detected by the windowing algorithm, we can see that actually the map is black. So these were currently actually some points that were detected by the windowing algorithm. They were false positives because the FFT does not detect any peak. And finally, if we go on the very bright spots, we can see and recognize the peak, which is associated to our metamaterial. In terms of quantification, the spectral method is able to quantify 65.8% percentage of positives, while the windowing only half. And if we take into account the number of pixels which were detected by the spectral method and the windowing method, this value drops to 19.3%, which means that the pixels that were detected by the windowing algorithm, there were also some false positives detected. So in conclusion, I have shown an approach based on acoustic metamaterials to develop new implantable sensing concepts. The temperature sensitivity does not change much with different media, and the resolution stays below 0.2 Kelvin in the case of the tissue. And finally, the sense localization is enhanced with a spectral analysis reaching a value 65.8% of positives detected. Our next steps are to use also phased array transducers to perform spatial averaging in order to improve the resolution, and also investigate other parameters of interest such as strain, which is also important in bone healing. And with this, I would like to thank all my collaborators in Zurich, the facilities the facilities of the clean room, and my student Yannick Merz, and our sponsors. Thank you very much.